notes within the examples that we're going to do. Okay, so there's note 1 here says that when we're trying to find a particular integral, we sometimes have to be careful that we don't duplicate a solution that we've already stated in our complementary function. So for instance, say I had been solving a non-homogeneous differential equation and I'd come up with two values for m when I'd solved the auxiliary equation where m equals 2 and m equals -1, and we would come up with this complementary function, a e to the 2x plus b e to the -x. Now, say that whatever the differential equation was, I had, say, an exponential that also had the power was 2x. Then what I would be required to do in my particular integral would be to keep that 2x as a power of the exponent and add a constant term. So I would normally think then of saying, well, my particular integral would be some constant times e to the 2x, because we would have to try and maintain this 2x here. But you notice that what happens there is that we're then duplicating one of the solutions, which we can't do. We want to try and maintain separate possible solutions. And so just as, if you think back to the fact that when we had the same values for m, so when you've got two identical roots, and we don't write down, so for instance, if we have m is 3, we don't write down y equals a e to the 3x plus b times e to the 3x. We actually have to do it as a plus bx. We have to create two separate terms. Otherwise, we'll only get one solution, and we need, in this case, two solutions. So what we do is we multiply one of the solutions by x, and that's a valid way. There's a relatively complex mathematical reason why. So we can do the same idea here. So instead of our particular integral being c e to the 2x, we're actually going to multiply that term by x, and so we're going to use cx e to the 2x as our solution. And what that does is it keeps our particular integral an actual different type of solution, a different form of solution to the kind of matching one that we've got in the complementary function. Next example has got a bit of that going on, and you'll be able to see it being used. Okay. Second point I want to make is not something we're going to go on to use certainly in our course, but it's worth considering, and just for a bit of information, you do get in differential equations f of x, non-homogeneous, f of x can be a sum of the three different types. It can be, for instance, a polynomial and a trig part to it. And in that case, what we would do with a particular integral is simply put together the different templates for the polynomial and the trig term. So you can see here we've got 3x plus sine 2x. So there's the polynomial part of order 1, and then the response that we have to the trig term is what we would do for that trig term. So we put them together, and we would still then go on and differentiate twice and substitute. So it's a bit more involved. We're certainly not going to get into that, but just for your information, it does actually happen. And last point to make before we go into the example is you probably predicted that we're actually going to, up until now, we've been finding general solutions, and we can actually find particular solutions if we're actually given some extra information. Okay, and the key thing is that we only start using that once we've actually got the complete general solution. So we don't think about the different conditions, values for y and dy by dx, all that kind of stuff, until we've got the general solution. So I'm going to go on and do example 21. There's another example 22, two more, and we're going to throw in a couple of these aspects into our work. Okay, so here we go, example 21. So this is a particular solution. We're back to a homogeneous differential equation, so that's a little bit easier. But we're given 3 bits of information now, which is different from a first order differential equation. We're given information about a value of x, and y and dy by dx. Okay, so when x is 0, y is 3. So that's one set, and we can double that up to say when x is 0, dy by dx equals 20. So we kind of keep those as separate pairs of information, and we'll come back to that. So let's have a look at the differential equation. It's homogeneous, as I say, so we can already find the auxiliary equation. I don't know why I'm using red. So we'll go substitute for m squared minus 10m plus 25 equals 0. I'm going to do my discriminant check. You might already have an inkling as to what we're going to find. Net b is negative 10, so we've got 100 minus 4 times 1 times 25, which of course is 0. So we've got equal roots, which means we're going to have to use the form of the solution y equals a plus bx multiplied by e to the mx. Okay, so we've done a little check of what's going to happen, looking into the future. So we factorize this, we're going to get only one solution. So I'm going to have to find the square root of 25 is 5, obviously, and we're going to have the same sign. Everything's going to work out, so they'll get one solution, m equals 5. Which means that we're on a homogeneous equation, so we can write down the general solution now, after having written complementary function for a few examples when it's non-homogeneous. General solution goes like this. We know the form is y equals a plus bx multiplied by e to the mx. We know that m is 5, which means that we've got our solution of a plus bx multiplied by e to the 5x. Okay, so that's our general solution. That's as far as we would go up until now. However, we have extra information that's going to help us find a particular solution. So, for a particular solution, now let's think about the information that we've got. The first thing we're going to think about is that when x equals 0, y equals 0. So we'll leave the dy by dx information for a minute. We're going to consider this. And if we substitute in, we can see that y is 3. Get it right. So if we're substituting into this equation that we've got here, then y is 3, and it means that a plus bx, well, we're told that x is 0. Okay, so, and e to the 5 times 0 is just going to still be e to the 0. That goes to 1. So we're left with here basically it says 3 equals a, or in other words, a equals 3. And there's our value of the constant a. We can then use the second set of information. What are we given about? We want to find the derivative. So we need we've got information about dy by dx, so we have to find an expression for dy by dx. So we've got y up here. So we've got the product rule going on here, a plus bx multiplied by e to the 5x. So I'm just going to do it quickly. If you want to write it out as u and v and u dash and v dash. So we're going to differentiate the first term, a plus bx differentiates just to b multiplied by e to the 5x, plus we're writing down the first term and differentiating the second, e to the 5x differentiates to 5e to the 5x, so that's using the product rule. Which we can then simplify a little bit. What have we got? Equals b times e to the 5x. We multiply that all out. We've got, well, the a is 3. Okay, so let's just stick this in. Okay, maybe we should have stuck 3 in at the very beginning, but there we go. And that gives us b e to the 5x plus 15 e to the 5x plus bx 5bx e to the 5x. Okay, that's as good as we can get. I suppose we've got b, we get 6. Now we can leave it like that. So what we're told that when x equals 0, dy by dx equals 20. So here's dy by dx on the left-hand side, which is equal to 20. And we've got b multiplied by e to the 5x, which is just going to be e to the 0, plus 15 times e to the 5x, which is going to be e to the 0, plus 5b 0 e to the 0. So of course that's going to be 0. E to the 0 is 1. And we end up just saying that 20 is equal to b plus 15, because they're both 1, which means that b is going to be 5. So we've got values for a and b, so we can say that our particular solution which we started off as being y equals a plus bx times e to the 5x. That's our general solution. We now know that a is 3, and we know that b is 5, and there is our particular solution. That's how we do it. So once you find the general solution, we just had to take the ability to substitute in, and first of all we just deal with x and y pair, and then we differentiate and look at the x and dy by dx pair, and that should be enough to go ahead and work out the particular solution. So a lot of stuff there. Have a look at that, try some examples, and then come back for the last one, example 22.